Good day to you. Today we are going to be covering the last section in Chapter 8, which is natural logarithms. But first, as my board here clearly indicates, we need to talk about the number e, because the number e is considered the natural number, and if you understand the number e, then the natural logarithm might make more sense. So, first of all, I want you to consider this function y equals 1 plus 1 over x to the x power. And this is somewhat of an exponential because the variable, the exponent over here, is a variable, even though there's also an x here. So what I want us to do, and you can do this, in the comfort of your own home, is to determine what the value would be for this function if x was 1. If x was 1, you would get 1 over 1, which is 1, plus 1, which is 2, and then 2 to the 1 power would be 2. And then I want to try 10. What would happen if x was 10? What about 1,000? What about 1,000,000? And you might be surprised. You might be thinking to yourself right now, this is 2. By the time I get to 1,000,000, it's probably going to be so huge, who knows what it'll be. So what I'm going to do right now is I'm going to go ahead and plug into my calculator 1 plus 1 divided by 10, which is 0.1. And that's going to be 1.1, and I'm going to raise that to the 10th power. And you get 2.59374246. Alright, so you went from an x value of 1 to an x value of 10, and it went from the y value from 2 to 2.59, roughly, okay? So we would expect that maybe when you get to 1,000, it's going to jump a lot higher. We'll see. So now we're going to go 1 plus 1 divided by 1,000, and 1 over 1,000 is 0.001, and so you take that, add 1 to it, and raise it to the 1,000th power, and you get 2.716923,932. Those are all the decimal places that my calculator will give me. Okay, so I don't know about you if at this point you're kind of thinking this is kind of weird. When you increased from 1 to 10, so 10 times as big, the value kind of went from 2 to 2.6. So we would have at least expected a larger jump, but when you have 1,000, which is way bigger than 10, you don't have that big of a jump. You go from roughly 2.6 to about 2.7. So you didn't go very much bigger. I wonder what would happen if I put in 1,000,000. So now I'm going to go 1 plus 1 over 1,000,000. 1, 2, 3, 4, 5, 6, 0. I'm sure I have enough zeros there. And then I'm going to take that number and raise it to the 1,000,000th power. 1, 2, 3 zeros, 4, 5, 6 zeros. And I get 2.718280,469. So I'm not going to bore you any further. But basically what you see is that as x gets really, really large, the y values are starting to approach a number. And believe it or not, based on that expression, that's basically what the number e is. So we can now say, and I don't know if you're convinced yet or not, but if you don't believe me, you can keep putting in really large numbers for x, like try, 10 million or something, and you will see that the number e is approximately 2.718. It's going to basically be asymptotic. We know that this is kind of exponential, and so we should expect that exponential functions are asymptotic. They approach lines, right? So in this case, this number approaches 2.718. And that's important because we know that, and by the way, this number is irrational. So there's no fraction that you can make that will equal 2.718. And this is approximate. It's kind of like pi. Pi is approximately 3.14, not exactly 3.14, and it never repeats. Same thing here. But we use 2.718 as the approximation of e. So that's what the number e represents. And if you look at this expression here, it kind of looks familiar to the simple compound interest formula you've probably done in Algebra 1 and even in middle school. We had a simple interest, compound interest formula, which is right here. And you can kind of see the 1 plus, if the interest rate was 1, then you could put R would be a 1. So you would get 1 plus 1 over n to the nt. And it looks very similar to what the letter E stands for, 1 plus 1 over x to the x power. So what I wanted to show you with this is, if you don't remember, I don't want to spend too much time on this guy, but basically this is for compound interest. We know that if the more times you compound interest, the more money you can make. If you have money that's being saved or whatever. So n was the number of compounding. So if you were compounding 4 times a year, it means that that's how many times a year the bank will take your account and multiply it by the interest rate. So if you have $100 in the account and you have biannual compounding, it means that twice a year the bank will take the sum of the money that you have in your account. So let's say you have $100 in the account. It means that the bank, let's say that you have a 10% interest, which is not going to happen, just to make this easy, at 10% interest, it means that if you started the account in January, sometime in June, which would be the first time of the year, sometime in June, they would take your $100 and times it by 10%, which is going to be $1. And so then they would add that amount to your account. So if you have $100 and you have 10%, so you get $10 of that. So now you have $110. And then sometime in December, because that would be 6 months later, they times the 110 by 10%, and now you have $11. So then you would have your initial 100, then you have the $10 that you added at the 6-month mark, and then you would have the $11 that you added at the 12-month mark. So now you have $121. So again, don't want to get too crazy into that if you don't quite understand that just yet. You can ask me in class, I guess, next class period. But basically, you get $121 after 1 year, after 2 compoundings. So if you compound 12 times a year, basically what it means is that after 2 months, you would have $121 because every compounding you're adding 10%. So if you compound every month, you're going to get the 121 after 2 months, not after a whole year. If you compound it annually, it's going to take you 2 years to get $121, and so on and so forth. So that's kind of the compound interest formula. But again, that's not what I really want to focus on right now. I want to focus more on the continuously compound interest formula. So whereas the simple interest formula has a lot of the same stuff, you have an A, you have an A, you have a P, you have a P, time is still time, R is still R. But what you will see that the big difference is the letter E here. The letter E kind of replaces the 1 plus 1 over n to the n power. If you think about the compound is the n. So if you had an interest rate of 1, you would put 1 plus 1 over n to the n. That kind of expression is being kind of replaced with this letter E because of what we just saw earlier, that this expression basically becomes 2.718. So we use that idea and we'll replace it in that formula with this one. And so now we have a continuously compounded interest formula, and A represents the amount in the account, P is the principal, of course E is 2.718 roughly, and your calculator has an E button, and then R, the annual interest rate, and then T, time in years. So I want to show you how that would work out. So here we have an example, and it's very important that you only use the continuous compounding formula when it says compounded continuously. If they had said it was being compounded annually or monthly or weekly, you would have to use the old formula. But in this case, it says compounded continuously. So we're just going to type in, we have, they want to know how much will be the account after 5 years. So we don't know the amount in the account yet, but we know that the principal, you invest $1,050, and then you have E, and then you raise it to the R power, But 5.5%, if you want to get that as a decimal, you just divide it by 100 or move the decimal 2 times over, and you get 0.055 t. And in this case, t is 5 years, so I can even go ahead and replace the t with 5, okay? And then I just simplify that. So I'm going to go, it's really important that you not go 1050 times e. I would do the e to the this power first. So I'm going to go, and on your calculator you will see the log button that you're familiar with by now, and right below it is the ln button, and if you hit second and then ln, you will get e with a little caret and an open parenthesis. So in that parenthesis, I'm going to type in 0.055 times 5, close the parenthesis, hit enter, and I get 1.3165, blah, blah, blah. I then take that and multiply it by 1050, and the amount that I have in the account after 5 years is basically $1,382.36. I rounded up because this is money. All right? And that's pretty much how you use the compound interest formula. Just got to get familiar with using the letter E when it's continuous compounding. So now you can try this guy, and then we can get back to why we're really here, which is logarithms. Okay? So I wanted to kind of recap just a little bit for you. You will remember that we already talked about exponential functions like y equals 2 to the x. You can have an exponential function with the base of e instead of 2. It's just you've got to get comfortable with the letter e and understand that e is not a variable, even though it's a letter. It's not a variable. We know what e is, and variables are things that we don't know. So this is not 2 variables here. E is just a number. It's 2.718. So you could even put something like 2.718 to the x power. Okay? But we use the letter e to denote 2.718. So if we have y equals 2 to the x, we've already talked about in the last sections that the inverse function would be log base 2 of x. Well, so if you have y equals e to the x, then you would expect the inverse function to be log base e of x. And that is actually true. And what I've written down here is that ln is another abbreviation that we just saw on the calculator underneath the log button. And ln literally stands for natural log. Some of you might already be in a Spanish class, maybe not, I don't know. But in Spanish, ooh, my battery is low. That's not good. Logarithm, waiting for the battery to come back. Hello. Let's see here. I'm going to grab a battery. Please hang tight there for me real quick. I will tell you that my board and I have a love-hate relationship. I haven't decided yet if I love it or hate it, but I'll tell you that I have these feelings about it frequently. Sometimes I love it, sometimes I hate it. Maybe at the end of the year I'll decide if I hate it altogether or love it altogether. But it looks like, here we go. So natural logarithm, as I was saying, talking about Spanish, because it might not make sense to you why it's natural logarithm. Why do they call it NL instead of LN? But it's actually Latin, and Latin is kind of trying to ask about the whole Spanish thing. When you describe things in Spanish, like a red car, like in English, you would describe the car before you say the noun, so the adjective goes before the noun. But in Spanish, it goes backwards. We don't say rojo carro, we say carro rojo. So it's kind of backwards. So just keep that in mind. And even though it says ln, it's actually natural logarithm. And ln basically replaces the log base e. So normally when you have to put like a little 2 there, you don't put a little e here. When you see ln, you have to know and remember that ln is log base e. So ln x. All right? And that brings me to what you can do with them. So aside from, you're probably thinking, oh, this is going to be a hard new lesson. It's not. All of the properties that apply to normal logarithms that we already learned also apply to the natural logarithm. So I'm going to show you that right now. You learned how to condense and how to expand logarithms in 8.4. And I'm just going to show you that you can still expand and condense logarithms if it has an ln. Just remember that ln is log base e. So the power property still applies here. So this would become ln 6 to the third power minus ln 8. And then because of the subtraction, that still becomes, the quotient property. And so you can get ln 6 cubed divided by 8. And then 6 to the third power is probably a really big number, 216. And then divided by 8, so then that becomes ln of 27. So nothing really crazy. And the cool thing about ln is that, like, you know how your calculator only works, I've told you so far that it only works in base 10, the LOG button. You've probably seen the ln button, so I actually kind of lied to you. There's two bases that your calculator works in, base E and base 10. Base 10 is called the common logarithm, and of course base E is the natural logarithm. Those are the only two logarithms that your calculator will work in, so I won't introduce any new ones to you in the future. So if you want to find ln 27, you don't have to change the base. All you have to do is use the ln button, type in 27, and it is going to be roughly 3.2958. Okay? So for that example, you're going to get 3.2958, sorry. Okay? So that's how you can simplify them. Now again, in this example, it didn't ask us to evaluate it. It just says to write it as a single logarithm. So this would technically be your answer. But I just wanted to show you that if you actually want to know what the actual answer is, it's 3.2958. And remember that what does that answer actually mean to us? It means that if I took e to the 3.2958 power, it would roughly be 27. And you can check it on your calculator that I'm not lying to you. So now, again, remember, I want you to do these problems. I want you to remember that all of these problems, you just treat them at normal logs. All the same properties apply, and then you can write them as a single logarithm. So then, of course, the next thing to do is to solve equations. In the last section, we solved equations with logs, LOG logs, and now we're going to solve equations with ln. So, but again, the concept is the same. You want to make sure that you can write it in exponential form, and it is helpful sometimes for you to, remember we said that ln really just means log base E. So I can rewrite this like this. It'll probably make it easier for you to remember if you rewrite it, but you don't have to. So if I write it log base E, then I can see that e to the fourth power is this. And we've done this before, okay? So I'm going to go e to the fourth power equals 3x plus 5 squared. All right? And then you can solve that by basically doing what you would normally do, which is to maybe square root both sides to get rid of the square. And then you'll get 3x plus 5. Then you want to subtract 5. And then, so that's going to be square root. And notice that I'm not going to put a decimal in until the very end. So this is where I'm at so far. I square rooted the e to the fourth, I subtracted 5, and now I'm going to divide by 3. So technically, this is the exact answer. X equals the square root of e to the fourth minus 5 over 3. But then if you want an approximate answer, I'm going to go to the calculator, second square root. I'll use the second ln button to get the e to the fourth power. And then I'm going to subtract 5 from that, and then I'm going to divide by 3, and I'm going to get 0.7964. And I'm not exactly sure how many decimal places they wanted you to use, but they used 3, so I'm just using 4 there. But there you go. That is how you can get your answer. So nothing really changes. You're still using the same little exponential form. Take a logarithm to solve it. You want to write it in exponential form, and then it's not that hard to solve. All right? So now we're going to have you solve a few. So there's that. And then I'm going to do backwards. So first we solved an equation that was a logarithm by using the exponential form. And now I have the exponential form, and I'm going to solve it by doing a logarithm. So what you want to do when you're solving these guys generally is to isolate the exponential part. So I'm going to move my 2.5. So let me get a different color here. I'm going to move the 2.5 to the other side. So 7e to the 2x equals 20 minus 2.5 is 17.5. And then I'm going to divide by 7. And I get e to the 2x equals 2.5. So now that I have the exponential part isolated, the next thing I do is take the log of both sides. Okay, so, and that can be interesting. We're going to do ln. I'm going to show you how this goes. So ln of e to the 2x and ln of 2.5. So I take the log of both sides. And as you know from before, the 2x right here is going to go to the front. So I'm going to get 2x times ln e equals ln 2.5. And what's cool about this is, at this point you could divide by ln e if you want to, but I don't know if you noticed this, but what does ln e actually mean? I'm going to come over here and show you. What is ln e? Technically, ln e is log base e of e. And you might not have noticed that right away. And this, I can tell you, is going to be 1 because e to the 1 power is e. So whenever you have ln e, it's actually just 1. So since ln e is 1, there's not really any need to divide by ln e. You can just cancel it out because it's a 1. And 1 times 2x is just 2x. So the only thing I'm going to be dividing by is 2 to get rid of the 2 in front of the x. So now my x value is ln 2.5 divided. So I'm going to use my ln button and put 2.5 in there. And then divide that result by 2. And I get approximately 0.4581. And that is how you solve an exponential using a logarithm. And we have one more example, and then we can call it a day. All right. These are your examples to your do-it-yourself problems, and then we can have our last example. And this is kind of it should look familiar to the first example that we did. You see the compounded continuously. So we're going to be using the PERT formula. By the way, I should probably explain that. I call this the PERT formula because, you know, PERT plus, the shampoo, kind of has this, you know, P-E-R-T, PERT. So I just call it the PERT formula. But anyway, we're going to be using this formula, but we're going to be using it kind of backwards in this case because we're going to be solving it using a logarithm. All right, and I'm going to show you what I mean by that. So an initial investment of $100. So initially, the principal amount of this investment, so that's P. This is P right here. It would help if you could actually see P. That's P. But now it's valued at 149.18. So it was 100, and now the amount in the account is 149.18. So we're going to call that A. That's the amount in the account. The interest rate is 8%, so there's my R. It's compounded continuously, so I'm going to be using the E. And that's asking how long has the money been invested. So they want me to find T. T is my variable. Okay? So let's plug in everything that we know. We know that A is 149.18. Initially it was 100. E, the interest rate is 8%, so you just take the 8% and move it. So it's going to be 0.08. And we don't know what T is. So right now I'm trying to solve for T, so you might be starting to see why I'm going to need a logarithm. This T needs to get out of the exponent. But before I mess with the exponential part, I got to get rid of the 100. So the first thing we're going to do is divide by 100. so that I get e to the 0.08t, like that. And then that's going to equal 149.18, 149.18, and divide that by 100, and I get 1.4918. All right? And now, if you take the log of both sides, I'm going to do the ln, the natural log. So ln of 1.4918 will equal ln of e to the 0.08t. And then, because of the power property, the 0.08t will come in front. So this will be 0.08t times ln e. And again, we already said that ln e is the same thing as 1. So really all you have is 0.08t on this side and ln 1.49 on the other side. So now to get rid of the 0.08, I divide by 0.08 on both sides, 0.08. And t is going to equal the ln of 1.4918 and then divided by 0.08, and it's 4.9997. So basically about 5 years. Okay? So how long has the money been invested? Roughly about 5 years, 4.999, so approximately 5 years. All right? So now you're going to do something similar in this problem. Just want to remind you that kind of similar. You have the initial investment. Now it's worth $315.24. But this time they're telling you what T is. It's after 7 years. T is 7. But what you're looking for now is the interest rate. You're looking for R. But remember that in the formula, R is in the exponent. So the one that I solved had a T. That's what I was solving for, but it's very similar. You're just solving for R instead of T. Alrighty? So once you've done that, you will have completed the notes for this lesson, and I will see you in class. And good luck.